bear with me as we do that. You'll see probably a notification pop up that the meeting is being recorded and that the meeting is being live streamed. As we do that, I see a number of you joining, and some of those names are familiar. Anshul, it's good to see you. Scrolling down the list. Daniel, pleasure. Would love to hear where folk are from. Please drop in chat. Chat is open. You're free to sort of chat with everyone. My name's Tyler. I look after developer relations at ClickHouse, and I'm based here in Amsterdam. Would love to hear from you where you are from as I let the rest of the world know that the webinar has started. And we'll get started here with the content in just a minute or two. Jose, welcome from Madrid, and Sergio from Toronto. Look at this, Georgia and Canada and Malta. I think Matthew perhaps has the best region of all of us so far. Amazing. So for those of you who are just joining, it's going to take us just a minute or two here to get started. We're letting some more folk join. We're also letting the world know that we are live, and I'm manically clicking in the background, posting on all of the social channels that we're live. Feel free, let your friends know that we're getting going. We have a number of people dropping in chat where they're from. It looks like Chennai and Kosovo and Brazil and England and Texas, and, Connecticut, and Edinburgh, and Scotland, and San Francisco, and Philly. I'm based here in Amsterdam. If you've just joined, feel free to drop in your location. One of the things to me that's incredibly compelling about what ClickHouse represents, I mean, open source projects in general, but ClickHouse in specific, is the opportunity to engage with passionate enthusiasts of real-time analytics, of databases, of data warehouses across the globe. And taking just this moment or two to look at those is really, it's exciting to me. It's compelling. All right, amazing. We have an immense amount of content. I have, while we were talking, posted in all the places. So Dimitri, if you wouldn't mind sharing, that'd be amazing. And we'll go ahead and we'll kick off and let other people join. As the share starts, just a couple of housekeeping items. As I mentioned, chat is open. Feel free to use it. We also have the Q&A widget. If you have questions, drop them in. We'll do our best to answer them sort of in text as we go along, but it may be that we have some time at the end. It will depend on how the content goes. And Dimitri, if you'd go to the next slide. One thing I do want to call out real quick is something I'm super excited about. If you happen to be in the US, within driving, hiking, flying, walking distance of San Francisco, May 28th and 29th, we're going to hold our first in-person user conference, Open House. It's a day of tech deep dives, of user stories, of hanging out with other folk who are deeply passionate about what ClickHouse is. Check it out, clickhouse.com/openhouse. We also have a CFP that's open as well. So would love to see you there if it's a possibility for you. And on the next slide, I'll talk a little bit about what we're actually going to cover today. So really, three main areas of focus in this call that we have once every other month or so. Today, we're going to start by diving in deeply into what warehouses are in ClickHouse Cloud, or what you may have heard us refer to in other calls as compute separation. We'll spend some time on the notion of ClickHouse Cloud scaling, and then dive deeper into Graviton and ClickHouse Cloud directly. So with that, I'm going to hand it over to the first set of speakers. Dimitri, do you want to kick us off for today?
Thank you, Tyler. That's amazing. Welcome, everybody. My name is Dmitry Pavlov, and at ClickHouse, I'm responsible for our internal data warehouse. It's a magic place, magic ClickHouse instance, where we collect all the data across the company and provide our internal users access to this data through various instruments like BI tools, ad hoc queries, etc. But for this particular feature that I will be sharing today, I was acting as a product manager, though I am not a product manager, just because I really wanted this feature to be in ClickHouse Cloud, first of all, for my internal data warehouse that I built in ClickHouse, but also, of course, for you, for users of ClickHouse Cloud. But first, let's speak about why actually you may need this feature, or maybe you don't need it at all. So there are three main use cases that were not covered by the classical ClickHouse Cloud architecture, and that we saw at our customers, both internal customers and external customers, that they would like to have covered. The first one is isolating writes and reads. It's a very common scenario. You have some ETL processes that are super important for you and you cannot miss your data. So all the insert queries should work very fast, very reliable, and they should not be disturbed by any noisy neighbor. For example, read queries that are generated by users, by ad hoc users writing physical queries. And everyone can make a mistake. Everyone can run a query with a, for example, cross join without any on clause in the join language. And this will cause the read operations to influence the write operations. The write operations can fall, for example, can fail with out of memory error, or they can work significantly slower than expected. Or the situation can be vice versa. Reads are super important because reads are generated by your business application, and your end users are actually using your business applications like some dashboards or some charts, etc. And you don't want these queries to be influenced by writes that are done in the background. The second use case is not so often, not so popular, but still we see. So if you have a large company, large enterprise, and you are administering a ClickHouse Cloud instance, you may need to separate your workloads between different departments, not only in terms of their compute resources and their performance, but also in terms of billing. So different departments accessing the same data, the same tables, may want to have different billings for their queries. So they would be able to say how much they spent for the compute infrastructure in the ClickHouse instance. And finally, the third use case is that there are different use cases inside one company, one ClickHouse instance. And some of this use case may require full high availability with three zones in different availability zones. Another use case, for example, ad hoc analytics that a person runs personally with his hands writing queries in some kind of IDE, for example. It may need only one node in one availability zone, and it's okay for this zone to fail in case of some disaster, for example, and to be restarted in a few minutes. You don't want to pay for the second node in this scenario. And if you take a look at the traditional ClickHouse architecture, the same architecture as every ClickHouse service has in ClickHouse Cloud, you can see that actually service consists of the compute nodes. Obviously, these are the nodes that are processing your queries. The shared folder in an object storage bucket. Basically, this is a folder with some security mechanism applied in the S3 bucket. The endpoint, a single endpoint that is pointing to node 1 or node 2, depending on the load balancing, and the keeper instance. So a set of keeper nodes. And you query the endpoint decides which node to use, and then the node goes to the object storage and gets your data. So this is a single ClickHouse service. Then what we introduce now is a warehouse. Warehouse is an entity that unifies multiple services into single warehouse. Sorry for my language, but still. And what changed here is that multiple services now can share the same keeper instance. So the keeper cluster is the same for multiple services, but all services have their own endpoint, compute nodes, and these compute nodes can be different size. They can have different number of compute nodes, but all the services will be querying the same data in the object storage. And now when you are querying your data, you can select between endpoints. Each endpoint will give you absolutely the same result. Same query will generate the same result in every service because you are querying the same data in object storage. But now you can select which set of compute resources you will be using. So that means that all services share the data, users, passwords, and grants. So obviously all the metadata is shared across the services, hypercluster, storage, and backups. But each service has its own compute resources, endpoint, network settings, which is very important because you may want to restrict customers or users from accessing service 1 and point them only to service 2, and also compute billing. So compute billing is separated per service. And from the UI perspective, it looks like this. You can see here we have two warehouses. The first one is data warehouse for tests US East 1, and this warehouse only have one service with the same name. But the second warehouse, it's actually our staging data warehouse. It's a real screenshot from my own ClickHouse Cloud account. And you can see that there are 4 different services in this warehouse. So there is the primary service, the service that was created first. It's called the same as the warehouse, data warehouse preprod. But then there is also preprod read-write 2, preprod read-write, preprod read-only. Services that you create in addition to an existing service to form a warehouse can be read-write or read-only. We will get back to this in maybe next slide. And you can also see that all services share the same region and the same cloud provider. Also, they share the same ClickHouse Cloud version, the same ClickHouse version. So for now, you cannot create services in a single warehouse accessing the same data in different cloud service providers or different regions, for example. In the future, this can also be achievable with the architecture that we choose. There are, however, a few limitations. These limitations, I hope, will be removed in the next few months. They are not blockers for the majority of the use cases that we saw, but still, the first service in the warehouse, we also call it the primary service, should always be up and should not be idled. If you want to stop or to idle the primary service, you need first to idle or stop all other services in the warehouse. The second one, and this is actually explained why we have read-only services now. All read-write services perform background merge operations, which means that if you create a primary service, the first service, which is obviously always read-write, and then you create a second read-write service, so you have 2 read-write services, both of the services will be performing merges. And you cannot predict which of these services will be performing merge for your query, because as you know, in ClickHouse, merge and the merge operation and the query itself are not connected directly. You may say that actually this brings us to a point where there is no 100% compute separation, and one read-write service can affect the other with mergers. And this is where read-only services come. When you create a read-only service, you can be sure that there will be no background operations in this service. This service will be purely dedicated for your read select queries, for your read-only, for your read operations. And by this, you can distinct reads and writes, reads from writes, or one department from another, if another department, for example, only needs to read data. So read-only services are completely isolated. Read-write services can perform background operations like merges for other queries from the other read-write services. And also insert, this also comes from the second bullet, but the third bullet is that inserts that are happening in one read-write service can prevent the other read-write service from going to idle, obviously, because they can cause merges on the second service, and these merges need to be finished before the service can go idle. And finally, there is a small limitation that we hope will be removed very, very soon, in just a few weeks, I would say. This is that if one of the subservices in a warehouse is idled or stopped, you cannot run create, rename, drop database queries. You can run create, drop tables, views, users, etc., no problem. But if at least one service is stopped or idle and you run create, rename, drop database, this query will not finish successfully, unfortunately, unless you set this setting. So this will be removed very soon. We already implemented the fix, and it's just we need some time to roll it out. How to start with this? If you want to test it out, so first you need an organization with at least scale tier. So you can start a trial, and then you need to select the organizational tier, and you can select the scale or enterprise. There is also starter tier. Starter tier doesn't support this compute separation feature. If you already have a legacy organization, then you have to upgrade to the scale or enterprise. And then you also create a service as usual, absolutely as before, same screen. But in addition to this service, later you will be able to create a secondary service. There are two ways to do this. Either you can click the plus sign on the existing service, and this will launch the screen that I'm sharing, or you can actually start creating a service, a secondary service as usual service, and then just click this checkbox, share data with another service, and select the first service in the dropdown. So this will bind these two services together to the same shared folder in the object storage bucket, and they will use the same keeper instance. And yeah, but they will have different endpoints and different nodes. And yeah, this is it. Have fun. The beauty of this approach of compute separation is that you can select different size of nodes for different tasks, different number of nodes for different tasks. You can select different idling settings. So the very popular scenario for me in our internal data warehouse is ad hoc analytics. And I can explain what it means actually. We have ETL tasks, and these ETL tasks for ingesting data and for building the marks don't require a lot of memory, but they are quite critical in terms of reliability, in terms of high availability. So we have 3 nodes running in different availability zones, but these nodes are relatively small. These nodes are just for executing ETL queries. And then there are ad hoc analytics who run their queries 5 by 8 from Monday to Friday, and they absolutely don't care about high availability because if their query fails, they just run it in a few minutes. It's not a problem to get another cup of coffee. But what they care about is amount of memory because their queries are quite large, a lot of joins, a lot of group bys on a large tables, and they need large nodes. So now I created a separate service for them pointing to the same data with only one node, but this node is huge. And I enabled idling for this node. So this node will go idle if there is no activity. And this is perfect for ad hoc analytics and perfect for ETL because now ETL works in a separate service, separate set of nodes. So basically, this is it. I'm happy to answer any questions if there are any. Tyler, what is the protocol here? Should I read the chat or maybe you can navigate me?
Yeah, please feel free to keep an eye on the chat as questions come in. Answer them there, answer things that may pop up in the Q&A widget. If we have time at the end, we may take some additional questions, but for now, Dmitry, this was incredibly exciting. The sort of power of isolating based on read or write or based on compute for different business units or number of nodes for number of tasks, like this is compelling and this is powerful. And I think this actually leads really well into our next section. So if you wouldn't mind stopping sharing, I'll ask the next speakers to share as well. Compute from compute separation, warehouses, incredibly meaningful, incredibly powerful. But I think the fundamental underlying question becomes, great, but how does ClickHouse Cloud actually scale? And Ashish is going to share with us a number of slides, and he and Manish are going to walk through sort of a deeper dive on what ClickHouse Cloud scaling looks like in detail. And I see your screen. I see some emails or Slack messages perhaps up there. And maybe if you click the magic slide share or screen share button, it'll pop up, eh?
Yep. One sec.
The joy of multiple monitors and presentation software. You would think that in the year 2025, it would be a solved problem. And yet, here we are. All right, awesome. So with that said, I'm going to go ahead and hand it over to Ashish and Manish to talk about this in greater detail.
Thanks, Tyler. Hi, everyone. Manish and I will talk about ClickHouse Cloud scaling. I'm currently a product manager here at ClickHouse, working on several aspects of our cloud product, including scaling. And I'll let Manish introduce himself.
Yeah, hey everyone. My name is Manish. I'm based out of Berlin. I'm an engineering manager here at ClickHouse.
Cool. All right. So before we get into sort of the updates, let's do a quick recap of how scaling works in ClickHouse Cloud today. So ClickHouse Cloud allows you to scale your service in both dimensions, vertical as well as horizontal. Vertical scaling is essentially resizing the replicas in a cluster to a larger size. we allow that both manually by using our UI as well as the public APIs, as well as you can auto-scale your service vertically. What that means is you can choose a minimum and maximum replica size, and ClickHouse Cloud will automatically, based on the load on the cluster, resize your replicas to the appropriate size. We also have horizontal scaling, as I mentioned, and that is available manually, where you can use a UI as well as the APIs to add additional replicas of the same size to the cluster. So both vertical scaling and horizontal scaling are available. And a quick note on how scaling or how auto scaling actually works in terms of like what metrics do we look at. So we look at both CPU and memory usage on the cluster. And depending on the higher of the two, we scale your cluster appropriately to the right size to avoid additional pressure on the cluster. There's a screenshot here which shows how vertical scaling and horizontal scaling controls are available in the UI, and we'll get into that a little bit more in the next few slides. So before we get into what we are improving with scaling, let's look at how scaling works in the old model, what I'm calling the old model. And that basically uses a break-first approach. Break-first essentially means we break or remove existing replicas before we add new replicas in its place. So in this example, we have 3 small replicas of 500 megabytes memory each. And if we see pressure on the cluster and we have to auto-scale, we will first remove 1 replica from the cluster. And then once we have removed that replica, we'll add a larger replica in its place. And we'll do this one by one for all 3 replicas until we end up with a cluster with 3 large replicas. So there are clearly some challenges with this approach today. One is because we are taking away capacity before we add it, we have to do it slowly. We cannot remove multiple replicas at the same time. So we have to do it 1 replica at a time, which causes scaling process or this operation to be slower than we would like, as well as we are taking away capacity when the cluster actually needs more capacity. So because of some of these challenges, we sort of re-architected how we would do scaling in ClickHouse Cloud. And we are moving to what we call a make before break approach for scaling. And what this essentially means is, let's say you have a 3 replica cluster with small replicas and you wanted to scale to larger replicas. We will quickly add 3 large replicas to the cluster. So the cluster will have an intermediate state of 6 replicas. And then we'll rebalance any metadata that's needed, which is a very quick operation. And then finally, we'll remove the 3 smaller replicas and end up with 3 large replicas in the cluster. As you can see, this means that we don't have to do this one by one, and we can very quickly add all of this capacity that's needed. And this allows for faster, more responsive scaling that lets us improve a host of other features. With that, I will let Manish dive deeper into some of the aspects of how scaling works and MBB.
All right, thanks, Ashish. So auto scaling in ClickHouse Cloud. So Ashish has just given a quick overview of break first and make first scaling mechanics. I'm gonna start by first introducing the architecture of auto scaling. And auto scaling is all about the automation or the automatic component in this, right? So all of the automation starts with data. And in our pipeline inside ClickHouse Cloud, it all starts with recommendation data. And that data comes from ClickHouse Cloud itself. So when you create a cluster and you run some queries on it, we're tracking the metrics like CPU utilization, memory utilization. ClickHouse does a lot of this tracking itself inside the system tables. We run ClickHouse Cloud on Kubernetes, for those of you who don't know that. We also look at the utilization data from Kubernetes. All of this data gets collected into a metrics database. Coincidentally, that's also a ClickHouse instance. And then we run the magic sauce here, which is the recommendation engine, right? So this recommendation engine looks at the historical utilization patterns of your data and then it produces recommendations about what should be your current size, right? This can be taken a step forward, maybe about forecasting, but currently we just look at, like, let's say, past few hours of data. And based on that, we decide right now you are under provisioned, and this is our recommendation to bring you to the right size. This is the first half of the story, right? So you create a recommendation, but then eventually you have to apply it. And that's where the story gets a little bit more complicated. So Ashish, if you could go to the next slide. Here we go. So as you can see from the, and this looks like a complicated picture, but hopefully I can do a good job in explaining it. Starting from the left, the recommendations that we just saw getting produced from your utilization data, along with the user-defined resource limits that in the screenshot Ashish showed you, you can just select, this should be my minimum memory size, and this should be my maximum memory size. All of those get fed into something called the autoscaler. And the autoscaler is responsible for basically executing the resizing of these replicas, giving you the right size for your ClickHouse cluster. And this step is exactly what happens one by one. And as you can see in this picture, the autoscaler is effectively doing a pod eviction. ClickHouse Cloud runs on Kubernetes, like I said. So in Kubernetes, if you want to resize things on the current version that we are running, the resize operation requires a pod termination and a restart. And if you see the third replica in this picture, that's getting evicted. And once it comes up, we have something called a mutating webhook. That webhook is going to basically hook into that pod, and then it's going to read the recommendation and bring it up in the right size. So in the example that Ashish showed, it was meant to come up with a size of 500 megabytes, but the webhook intercepted it and said, no, 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 you need to come up with a size of 1 gigabyte, right? So that's the mutation that happens. And once that mutation is successful, the replica gets resized, and then we repeat this step like 3 times eventually, and you get a bigger cluster. And that's the architecture of how our scaling behaves. And this behavior, this diagram is actually the same whether you scale automatically or manually. So if you don't have an auto scaling enabled, if you just want to resize manually in your own control, it will still happen the same way. It's just the input is something else, the trigger is something else. Maybe we can go to the next slide, Ashish. Right. So Ashish mentioned something about break first model, right? And so why is break first slow? It's slow because of multiple reasons, right? So because of reliability, like we run a standard production tier service that gets run in 3 availability zones inside ClickHouse Cloud. And we don't want ever it to be a case where more than 1 replica is unavailable at any given time. So we have something called a PDB, which for the Kubernetes enthusiasts among you will know is the pod disruption budget. And we only allow 1 replica to be unavailable at any given time. So in this example, because the PDB is set to 1, our systems are going to respect that setting and resize 1 at a time, and that is a slow process. Something that's not visible here, but it's important to note, is the termination is not instant, right? So you might have, for example, a backup running on replica 3, or you might have a long-running query running on replica 2. And once you start a scaling operation and you want to resize that cluster, it's not like we're going to interrupt that backup. So this process can take some time. And if you have a long-running query, we want to kind of gracefully terminate your server. So we give you some time, and in the worst case, we give you like 60 minutes to make sure that your queries can successfully process, and then we go ahead and terminate. What this means in practice is that in the worst case scenario, it might take 3 hours for you to execute a scaling operation, and that's obviously terribly, terribly slow. Ashish, next slide. Okay, the other problem that happens during a break first model of scaling is, as you can see, the third replica is getting restarted. But of course, the customer might also might have the same load or even increased load during that time, because, hey, probably you're scaling up because your utilization is trending upwards. If your utilization is trending upwards, we are receiving more load, and then we immediately restart your replica to scale you up. But the implications of that is the other 2 replicas start receiving that extra load, and in the worst case scenarios, they can also just crumble under the pressure, right? So 1 replica is getting restarted, the other replica crashes because it couldn't handle the load, and now your cluster is in a really bad situation. So these are the situations because of which we were really not happy with the break first model, and we wanted to kind of do something better. And that better way of scaling is make before break. So next slide, please. Okay, so tangential things here. Now we're getting into the weeds of how Kubernetes works and how we kind of use our in-house ClickHouse operator to do Kubernetes things. So inside our ClickHouse Cloud operator, we use something called a stateful set, and the stateful set in turn owns the server pods. Of course, they are binded to PVCs or like EBS volumes, which have the metadata that needs to get synchronized. This is kind of just to set the context of why, we need to implementing this change has not been trivial, even though we know that a lot of customers have asked for it. Maybe next slide, Ashish. Yeah, so in the earlier model, in the earlier make first model, what used to happen was that this single stateful set would control all three replicas. So if you were to ever provision ClickHouse Cloud, you would see the host names be like server 0 or server 1, server 2. That 0, 1, 2 suffixes, those are coming from a single stateful set. But of course, this comes with a challenge because of which implementing a make before break model was not trivial. And I'll get to why that is. Next slide. And this is the reason why stateful set scaling behavior prevented us from implementing make before break. So as you can see, if you follow from left to right, as you increase the number of replicas or as you make more replicas, you start with servers 0, 1, and 2, and then you add 3, 4, and 5, right? What this means is, of course, you get more capacity, but then if you remember how make before break is supposed to work, we want to take away the old, smaller replicas, right? And we want to preserve the newer replicas to give you better capacity. That is not possible with stateful sets because of various technical reasons I won't get into, but long story short, it's about ordinal. So when we scale in or when we dial down the number of replicas, instead of taking away 0, 1, 2, it would by default take away 3, 4, and 5. It's a very irritating problem, and it took us quite a long time to work around this, but we'll get to what the workaround was. Next slide. And the workaround was something we like to call multi-stateful set or multi-STS, where instead of a single stateful set owning all three pods or all three server replicas, we now have one stateful set, each in turn owning its own pod. And this gives us the flexibility so we can just arbitrarily add and remove pods without worrying about the order. And that allows us to do make before break. Next slide. And this is what it looks like in the end, right? All of that complicated story to get to this simple, nice result, which is that now we can just add more capacity. So you start with like 16 gig replica each, and then you immediately add 32 gig replicas. You scale up, and then you gracefully terminate the 16 gig replicas. And by the end of this operation, you're left with the 32 gig ones. And this is much faster. You're not doing anything which is one at a time. You're not putting any additional pressure on the remaining replicas. So scaling is now much faster. And fun fact, we also use it for upgrades. So I think in the new tiers that we have introduced, even like ClickHouse server upgrades, which would also previously work in the same way, which is taking away one replica, upgrading it, and then bringing it back, and then upgrading the entire cluster one at a time. Now we could just do it like this. We could just add 3 replicas, which instead of like 16 and 32 gigs, those could be version 1 and version 2, for example. And then you just use make before break to do the upgrades. I think that's all I have. Ashish, over to you.
Thanks, Manish. Thanks for the detailed overview of make before break. And I guess one more thing I want to add to what Manish said, because we are able to add this capacity quickly, it allows us to be very, more aggressive with our scaling thresholds that we use. So this allows us to really closely match utilization to cluster allocation. With that, let's take a quick look at horizontal scaling. So horizontal scaling, basically how it differs from vertical scaling is that it allows distributing the workload into a large number of small replicas, and this provides for better fault tolerance. In general, horizontal and vertical scaling kind of help with slightly different kind of workloads. So workloads that need a lot of resources from single machine or single replica, like a memory-intensive query would benefit from vertical scaling. And workloads that have high concurrency needs, such as wanting to ingest a large amount of data, will benefit from the parallelization that you get with horizontal scaling. And this is a quick screenshot of how horizontal scaling works from our UI. You can basically just choose a number of replicas that you desire for your cluster. And we will resize the cluster based on that allocation, that choice. And then this is a screenshot of how horizontal scaling works from our APIs, where you can change the number of replicas in the API call and resize your cluster. With that, Tyler, I'll hand it back to you.
Amazing. Thank you so much. Manish, Ashish, incredibly exciting. We've talked about compute from compute separation and the ability to optimize for your workload. Ashish, you can stop sharing at your leisure. And we've talked about scaling. And those two things in combination really define how you choose to deploy ClickHouse Cloud in your environment. And that's incredibly powerful. But a question many people ask us is well taken, which is how do you, ClickHouse, actually architect the underlying substrate of a cloud provider? And for that, Kaushik and Alexei are going to join us and talk in greater detail about Graviton and ClickHouse Cloud, the impact that it's had, the exploration that we've done, what it looks like as a SaaS provider to actually adopt a new architecture and deploy it. So Kaushik, at your leisure, it'd be great if you can share the slides.
Yep, just 1 second. Okay, hope you can all see my screen. Hey everyone, I'm Kaushik. I'm an engineering manager here at ClickHouse as well. And I have with me Alexei. Alexei, if you want to introduce yourself.
I'm Alexei, ClickHouse co-founder, ClickHouse developer.
Awesome. Cool. Today we'll be looking at Graviton and ClickHouse Cloud. But before we get too deep into that, let's dig a little bit into what ARM versus x86 64 are and why it matters for us, and then we'll go into the details of Graviton. So there are few subtle differences between major differences between how x86 and ARM kind of work. So ARM basically uses a simpler instruction set, it's called RISC, versus x86 64's complex instruction set, CISC, right? As an example, on x86 64 you have different SIMD instructions like AVX512. On ARM you have Neon. And a lot of modern databases rely on these native features to kind of get their inherent performance, like ClickHouse does too. And before we can start supporting ARM, we have to do a lot of changes to enable the support. And one of them is first need to compile for ARM. And for that, you will need to compile on an ARM toolchain. It either has to be on like cross-compilation or native compilation. And then we get into Graviton. So Graviton is AWS's ARM processor. So I think it was through an acquisition that AWS started supporting ARM on their cloud. So it started in 2018, and now we are in 2024. We have Gen 4 or Graviton 4. ClickHouse has native support for ARM, right? And it's the user doesn't really have to care about this as long as they run this curl command. We fetch the right binaries for you, and we run ARM builds for you. So then let's quickly look at the types of instances we have, right? So starting with Graviton 2, we have various instance types here, right? Like, for example, for compute optimized workloads, you have the C6G series. C6GN gives you enhanced networking. C6GD gives you local NVMe, which is great for caching and optimizations that we do as well. The M series gives you more like a balanced computing memory. T series is for burstable workloads. And then if you move on to the Graviton 3 series, we have the same, but the 7 comes in there, and for Graviton 4, it's 8. The naming conventions are essentially talking about the series here. 6, 7, and 8 talk about 2, 3, and 4 versions of Graviton. G is the Graviton here, and D means that you have NVMe or attached disks for you to use. With that, I'll be passing on to Alexei.
The first build of ClickHouse for ARM appeared in 2016, so about 9 years ago, even before ClickHouse was open sourced. But it is not enough to build a software for a different architecture and call it a day. We also had to implement to make it pass all continuous integration tests, to actually pass it continuously for every commit and every pull request, to publish builds from the continuous integration, to make all the required optimizations, including specific optimizations for ARM Neon. And also, it is not just a single architecture. We have compiled and tested it on different and even weird systems you won't typically find in data centers. Like we have compiled it for Android phones, and ClickHouse works there. We have run it on Raspberry Pi, and it also works there. And we tested it on a few server vendors. But the most interesting is obviously to test it on all generations in AWS. 2 years ago, ARM was declared production ready, which means everything that we do for x86, we also do for ARM. We support all the functionality, all the libraries that we have. And you can even mix different architectures on the same cluster. And the servers will work together. Next slide, please. Let's take a look at the most interesting stuff, performance benchmarks. And let's compare different generations in AWS. To remind, there are 4 generations. The first generation you can see at the bottom, it was A1 servers. It was like a prototype. Not so decent single thread performance and not so large amount of cores, but still useful for some like ad hoc tasks, scripts, and so on. The second generation that you can see under the names C6G, R7G, etc., was much more advanced. It was comparable with Intel and AMD servers by throughput, by overall throughput, but the performance of single thread, single core was still slightly less, while these servers provided advantages on price performance. From the third generation, all the problems have been resolved, and even the single thread performance was similar or even better than for the same generation of Intel and AMD servers. And last year, we also get 4th generation, and we were among the first to test it for performance when it was in review. And you can see that if you compare something like R7i, the 4th row with R8G, so I is Intel and G is Graviton, you can see the difference about 40%, which is significant. Next slide, please. And one interesting thing to do is to take our performance benchmark, which is open sourced and available under the name ClickBench. When you search for ClickBench, you can see it. Run it in a specific mode when we take all the queries and run them in parallel to utilize the server for the maximum capacity. And if we compare the same generation of Intel and Graviton, we can see that the number of queries per second is 25% higher on Graviton, but the cost is 15% lower. And this is for Graviton 3. On Graviton 4, it is way more significant. It is more than 1.5 times better QPS with still less cost. Next, please. Let's take a look at one practical example from our infrastructure. We have our cluster where we store all the results from our tests, all the logs. It contains tens of trillions of records, 65 terabyte compressed data. And this is even outdated. So it was like 4 trillion records half a year ago. Now it is more than 10. And more than petabyte of uncompressed data. And I picked one heavy query. And I ran this query before migration of this cluster to Graviton and after migration of this cluster to Graviton. By the way, this infrastructure runs in ClickHouse Cloud in our staging environment. So for internal stuff, we also use ClickHouse Cloud. Next, please. And this query scanned slightly more than 1 trillion records in about 1 hour. And this is before the migration to Graviton. And the question is how faster it became after the migration. Next, please. And it ran in less than 1 hour, about 10% faster. And it is a good result. But actually, I was questioning why only 10% faster, why not 25% faster as in our capacity benchmark that I showed. And I figured out that this query was mostly network bound. And when I tested on CPU bound queries, I got this 25% performance improvement. Now, next, please. Back to you, Kaushik.
Yep. Yeah, so we started migrating all our ClickHouse Cloud instances to Graviton. And as you can see, starting in the month of June, right? Like we started migrating them. And over time, we have majority of our fleet running ARM. So we have 82.68, 82.7% nodes running on the Graviton instances. And we had to pick and choose the various instance types depending on their availability in the various regions that we operate in. And we still have a small Intel footprint, and that's because of some restrictions in regions or the capacity that we really use. And over time, the plan is to migrate both Keeper and Server, all of them, to the Graviton instances. And yeah, that's mostly what I wanted to cover. Hopefully, this gives you some insight into how we use Graviton at scale and how ClickHouse was made to run well on Graviton. Back to you, Tyler.
Amazing. Thanks, Kaushik. And you can stop sharing if you'd like. There are a couple of questions that have come through. We've answered a number of them in chat already, but I'm going to bring up just a couple of them. And anyone who's on the call, Ashish, Manish, you're still here, Kaushik, please feel free to answer. We're going to start with one that's a bit detailed. That says, are you leveraging NVMe disks for caching object storage in ClickHouse Cloud? And how do they compare with EBS disks? For example, C7G versus C7GD nodes. Does someone want to take that one? Alexei, I see you raised your hand.
Yes, we do locally attached NVMe disks for caching. And if you compare with EBS, you will see that NVMe are better for overall throughput, for latency, and also for cost. If you happen to manage your own infrastructure and use EBS, you have to pay for additional IOPS. You have to pay for capacity, and you get, by default, you get these disks replicated, which does not make sense at all for caching. So combining the fastest available storage for caches, which is ephemeral, and the most durable storage for actual data, and combining it in a way that you get 100% durability on inserts, but also you get write-through cache and the best possible performance on selects. It is like the ultimately the best solution.
Gotcha. That's incredibly helpful. Thank you. Thank you, Alexei. A question related that came through in chat is there a way to request Graviton 4 in cloud when you're in a region where there's plenty of availability of those chips?
Graviton 4 is currently available in limited number of regions. And in many cases, it is difficult to allocate enough capacity, especially with servers with these local SSDs. So by default, as of today, we don't provide Graviton 4 if you use ClickHouse Cloud in self-service mode. Also, there is an enterprise tier where special configurations are possible.
Amazing, thank you. And Alexei, maybe this is it's a bit of a departure, but I have a feeling this is a question you'll be happy to answer. Is there an alternative to materialized views when you're replicating incoming data to ClickHouse Cloud tables as part of the migration process?
Yeah, one interesting possibility is to use distributed tables. So you create distributed table that points to ClickHouse Cloud. And when you insert into this distributed table, it will insert data to ClickHouse Cloud, and you can even make it in a way that it will insert both in your local instance and into ClickHouse Cloud for easy migration.
Perfect. And then I guess the last question, and you can answer this in the way that you see fit, but it makes sense to bring it up, is whether we see performance differences between different cloud providers when using similar resources.
Yes, we observe some difference. Also, different cloud providers are similar in performance of similar instance types. You can look at ClickBench, benchmark.clickhouse.com, and filter by ClickHouse Cloud entries. And you will see a comparison between AWS, GCP, and Azure. Sometimes there could be a bit of variance in the results. So one day they could be slightly up, another day slightly down for unrelated reasons. But in general, it is possible to compare different cloud providers. It is actually very interesting because while similar machine types have similar CPU and memory throughput, there is a difference in object storage. So S3, GCS, and specific, especially Azure, are quite different.
Amazing. And Alexei, you mentioned a couple of times, and you showed a link to it, ClickBench. We've got 4 minutes left. There's not a ton of questions. Do you want to just touch quickly on JSON Bench, given that JSON came up as a question earlier? Do you want to just mention it?
Yeah, recently we released a new benchmark, an extension to ClickBench, named JSON Bench. You can just type JSON Bench in search and you will see it. And we compared a few different databases for specific task for analytics on top of a large volume of JSON data. So if you have like data about e-commerce purchases in a JSON, and you have billions, maybe trillions of these purchases, or you have a social network and events on social network. And by the way, the data set that JSON Bench uses is open data from Blue Sky. And we compared ClickHouse, MongoDB, Postgres, Elasticsearch, and even DuckDB. And the results were quite surprising. It's much better if you look by yourself, but okay, let me tell you. We did not surprise that ClickHouse is the first. We knew it because we implemented JSON data type from first principles, like the best possible as it could be. So ClickHouse is the first, but the surprise was how big is the gap between different systems. We heard that MongoDB is a good database for JSON, unless you do analytics on JSON. if you do analytics, MongoDB is not a solution at all. You already know that Postgres has a quite sophisticated set of capabilities for JSON with the JSON-B data type, and it can even outcompete Mongo, but it cannot compete with ClickHouse on analytics, not even close. And Elasticsearch showed quite good results if you compare to Postgres and Mongo, thanks to indexing, but not even close to ClickHouse. There is still a huge difference, and it is an order of magnitude difference. So it's a difference like between possible and not possible. It is possible and very practical to do analytics on a large amount of data, JSON data in ClickHouse, but it is not practical to do it in any other system that we have found.
Makes sense. Thank you so much, Alexei. I know it's been a thing that's been of import to you recently, and given that the JSON question came up, I thought I would bring it up. We're coming to the end of our time together. Firstly, let me say a thank you to all the folk who presented content and slides to understand how you can take ClickHouse Cloud, how you can separate compute from compute based on your workload, and then how you can scale both horizontally and vertically based on your workload gives you the levers you need to optimize for the use case that you're building on ClickHouse. And I think understanding how we think about deployment of capability like Graviton, et cetera, is deeply important so that you know that we continue to invest into the future of the product. Most importantly, however, those of you who are watching this now live, thank you. Those of you who are watching it in the future on recording, thank you. It is you who make the work that we do deeply meaningful. If you enjoyed today's talk, if you're interested in looking at the code, go to GitHub, github.com/ClickHouse. You'll find the ClickHouse repo. Give it a star. You can see what we're up to. You can see the changes that we're making. You can see where we have meetups and events that are upcoming. Things that are near you. And as I mentioned at the beginning, we do indeed have our first user conference in person in San Francisco, clickhouse.com/openhouse. And if for some reason we missed your message, if you want to chat with other folk who are like-minded about technology, go to clickhouse.com/Slack and join our user community. We look forward to the next time that we get together, and keep an eye out. In 2 weeks, we actually have a release call for the next release of ClickHouse, which we do on a monthly cadence. So feel free to go to the website and register for that. Until then, thank you so much for your time.